A very good afternoon to one and all. I, Chetana HD, Assistant Professor, Department of Computer Science and Engineering, take this opportunity to welcome you all for third day workshop on network simulators. I extend my warm welcome to our today's resource person, Dr. Pradeep Kumar TS, ACM Distinguished Speaker, Associate Professor, IEEE Senior Member for today's workshop. I welcome you, sir. Now I request Dr. Pradeep Kumar TS to take over the session.
Yes, thank you, ma'am. So, good afternoon, friends. In continuing continuity of the yesterday's session, so we will be dealing with a new Manet routing protocols. So, what are the different Manet routing protocols available? So, how can we simulate those routing protocols? So that we will be discussing for the today's session. So, in this session today, so the date today is 16th October 2020. So, 2 p.m. So in this day, we will be seeing Manet routing protocols. See, whatever example I'll just quote here, or whatever example I'll just tell you here. So there are so many examples available in NS3. So to number it, so it could be around 200 plus of examples in all the networking. So you take 5G networks, you take 4G networks, and you take satellite networks, you take routing protocols, you take sensor networks, even IoT, 6LoWPAN. So and energy. So there are so many amount of source codes available. So only thing is we have to experience it by running this protocol, and if at all if needed, we can able to modify the protocols as well. Okay. So in this manner routing protocols, so such a very long protocol, you please understand this protocol in a greater depth. So that one example is enough for you to produce multiple results. So you can produce multiple results. You can produce multiple research contributions through this one single file. So this is what I am going to explain you now. So in Manet routing protocols, Manet means we call it as mobile ad hoc networks. Okay, so this called we call it as manets. So manets means it is the wireless networks that move. That's why we call it as a mobile ad hoc networks. So we have multiple other things as well as available. So WANet is vehicular ad hoc networks. This WANets. Now we have FANETs also. FANET is flying ad hoc networks. So we call that as drones or UAV or drones. So So we have these things available here. But in NS3 we have this Manet and Manet right away it's available. But FANET can be experimented with the help of some different mobility modeling. Okay, with the help of some mobility modeling, we can test FANETs as well in NS3. Okay, so now we will just go through these manets. So what is a manet? So how in what way we just form a network? So mobile ad hoc networks means, so usually manets have two categories. One is ad hoc based, that is infrastructure, and the ad hoc mode. Infrastructure mode, ad hoc mode. So infrastructure mode means it will have a routing router, router or gateway. Ad hoc mode means no router or gateway, no gateway. They form the nodes, form the network themselves. So this is what we call as ad hoc mode. So in this ad hoc mode, how can we simulate the network? So that's what we are going to see. So what are the different protocols available? So for this, in the ad hoc mode, we have various protocols under this ad hoc mode. So what are the protocols? So we have the protocol called as AODV. So AODV is ad hoc on demand distance vector protocol, that is AODV. Then we have DSDV called as destination sequenced. Distance vector. This is DSDV, and we have DSR. We call it as dynamic source routing, and we have OLSR, optimized link state routing. So this is what these are the four protocols. Generally, we talk about mobile ad networks. So these are the four protocols comes to our mind. So each and every protocol have their own pros and cons. So we call this AODV and DSR comes under reactive routing protocol. Whereas OLSR and DSDV proactive routing protocol. Routing protocol. So reactive routing means so they are dynamic. So this AODV and DSR, they are dynamic. They select the route based on the need. So that is what the reactive protocol. So these two select the route based on the routing table. So that's what the difference between these two. So usually AODV and DSR, they are reactive routing protocol. So that means the route will be selected based on the need. Need means the nearest node. Need in the sense that one method is the nearest node, or node with good energy. So anything. So we can able to customize anything. So nearest node or node with good energy. So routing table means purely based on the table. Purely based on the routing table. Okay. So this is what this protocol. So we can discuss this more on theoretical aspect of it. You can discuss it. You can read any documentation about AODV and DSR. It's a very long topic. But to just to give a glimpse of it, so in what way AODV performs well, in what way DSDV or OLSR performs well. Okay, so AODV we can say it is one of the optimal protocol for Manet. So already results are there. There are so many literatures are there that claims that AODV is one of the best protocol available, because the routes will be selected based on ad hoc mode. That means every packet can be sent, may not be sent in the same path. The path can be keep on dynamically changing according to the mobility of the nodes, according to the packet it is generating. So that's the way the AODV is on demand. So that's why the name called as ad hoc on demand distance vector. So whenever there is a demand, the path will be selected, the route will be selected. DSR in the sense that dynamic source routing, this protocol what it says is it will compute all the routes. So DSR computes all the routes from a node to the destination. And if there are 100 routes, all the 100 routes are stored in the cache. So DSR uses caching for the paths. Okay. So if any route fails, the alternative route will be taken from the cache. So this is how the way the DSR works. So whereas in VVCE, so the DSR, if any route fails in DSR, the alternative route will be taken from the cache. So out of 100 routes, the remaining 99 routes it will be taking. So that's what we call this DSR, dynamic source routing. Okay, but dynamic source routing will be taking more space. It will be bulkier because of the storing the cache. So all the path, the route, everything will be stored in the cache. So because of this, DSR and AODV perform the same method, same way, but AODV it don't maintain any cache memory, so automatically it will be selecting the path according to the demand. So that's why it is called as on-demand routing protocol. So these are the differences. But here OLSR and DSDV, it is link state routing means, so for between each and every node there will be a link from one node to another node. That link will be stored in a data structure. So based on this routing, the OLSR will work. DSDV is destination sequenced. So from one particular node to another node, so how the route will be forming, there will be a routing. So based on the routing table, each and every node will be sending the packet based on the next node available on a routing table. If suppose if the node is dead or if the node is not available on a particular location, so the routing table will be calculated again, recomputed again. So routing table recomputed, routing table will be recomputed or calculated on a timely basis. So frequently the routing table will be computed or recalculated or recomputed. So based on the nodes availability. So if the node is not available, if the node is dead, if the node moved to different location, so during those cases it will be computed. So having said that, these are the four protocols. Now we will go to the how we can use this protocol for our result analysis. So maybe it will take just for understanding the code, it will be taking around 45 to 1 hour for understanding the code. Afterwards, we will perform some results, some analysis we will do. So there are so many things we can able to do on this particular routing protocol. Okay, so we'll go through this. So first I will open this. Now we'll go to NS3 on Manet routing. Sorry, compare. This is a protocol. So first step one is open a terminal. Okay, step two, I'll go to step two. What I do is I'll go to CD NS hyphen all in one hyphen 3.31 NS hyphen 3.31. So 3.31 is the latest version of NS3 that I have downloaded from the internet from NS3 website. So you can use the same thing. So then after that I'll go to examples. Then we have example slash routing. Okay. So then when you type uh, file comparison CP copy Manet routing compare.cc. So this file should be copied. Okay, I'll put like this. Scratch folder. Okay, so we will just copy this file to the scratch folder. So Manet routing compare.cc to be copied to the scratch folder. So now this is what we are going to do. I'm opening a terminal now. This is a terminal. CD NS all in one. Then CD NS 3.31. CD examples routing. We can see there are multiple files available. So there are so many things. So we are going to have a file called as Manet routing compare. So this is a file Manet hyphen routing hyphen compare.cc. So what I do is copy this file. So I want to go to this folder NS 3.31 slash scratch. So double dot slash. So double dot means previous directory and one more previous directory. So first double dot will be going to examples folder. From there it goes to 3.31 folder. Now I will type scratch. So in this I am going to copy this file. So I just copied it. So file copying is done. That Manet routing compare.cc file is been copied. Okay. So now I'll just go back to this folder. I'm just in this folder now. Now gedit. So I'm going to open this file gedit scratch Manet routing compare. So you can see here scratch slash Manet routing hyphen compare. Okay. Just opening this file. So this is a example file. So almost around 400 lines of code. So the total number of lines is around 399. It is 400 lines. So we'll understand each and everything line by line. We'll go through the codings, and then I'll make you understand what does it mean. So what does this comparison means? Okay. Okay, seems to be so bigger program, but once you understand this logic, you feel, oh, such a easy example here. Okay, right. Now this some documentation there. Just please listen to the documentation in the beginning. This example program allows one to run NS3 DSTV, AODV, or OLSR under a typical random waypoint mobility model. So okay, so first what I do is to make your understanding. So I'll just copy some of the parameters, and then I'll routing parameters. Usually you can see in any journal paper or any journal work, they will be putting a tabular column of what is the parameter you are testing. So that is what is routing parameter. So column routing parameters, and first one is mobility. What is it? Random waypoint mobility model. So it is, sorry, mobility model. It is random waypoint. Okay. So you can put it as a tabular column, or you can use it like this. Okay. So this is the mobility model. So next thing is, by default, the simulation runs for 200 simulated seconds, of which the first 50 are used for startup time. The number of nodes is 50. Okay, so number of nodes 50. So number of nodes will be 50, 50 numbers. Then total simulated seconds is 200. So total simulated seconds 200, but we will be changing this value because for 200 it is taking so much time to run the simulation. So we will change this value. So instead of 200, we will change this value to something else. Okay, so total simulated seconds. So next thing is the first 50 are used for startup time. Anyway, we can use that startup time. 50 seconds. You can use the unit as 50 seconds. That this will be 50 seconds, 200 seconds. Okay. So next thing is nodes move according to random waypoint mobility model. So this we have already seen this with a speed of 20 meters per second and no pass time with a x and y of 300 cross 1500 meter region. Okay. So speed of the nodes, speed of the nodes is 20 meters per second. Okay. So then x and y will be x in meters. It's around 300 meters and y in meters. So it is a two-dimensional network. So 1500 meters. So please remember, so 300 meters on the x-axis side and y on the 1500 meters. So your simulation will be looking somewhere like this. So this is what your simulation will be looking. Okay, so this is 300 cross 1500 meters. Okay. So it will be like this. So this side 1500 meters, and this side 300. Okay, so this is the way that we can design the network. So sorry for the scribbling here. I do not get any good scribbling software. So anyhow, this is the x and y. So y is around 1500, x is around 300. Okay, so that's what routing parameters. So please remember, I am just helping you on how I can able to run the results, how I can able to plot the results, how I can able to do a research work using a particular code. Okay, so after experimenting it. So this thing. So next thing is the Wi-Fi in ad hoc mode. So the Wi-Fi here in ad hoc mode, the 2 MB per second at the rate that is 802.11b. So this is on 802.11b on ad hoc mode with a rate of 2 MB per second. So megabits per second, and a freeze loss model. Okay, so we have so many things here. So data rate Wi-Fi is 2 MB per second, 2 Mbps. So MAC layer is IEEE 802.11b. Okay, so B, then propagation loss model. So propagation loss model is, we can copy this freeze loss model. So the transmit power is set to 7.5 dBm, decibel meter. So transmit power. So power during transmission, it is on a constant value of 7.5 dBm. So decibel meter, it is called as decibel. Okay, so this is what the unit. Okay, so many information. So please remember, half of the result, half of the examples we can identify once we just understand the concept well, and then if we write it separately down, we can able to understand what is really about the simulation. Okay. Okay. So now it is possible to change the mobility and density of the network by directly modifying the speed and number of nodes. So you can number of nodes you can adjust, and the speed also you can adjust. It is also possible to change the characteristics of the network by changing the transmit power. So you can change the transmit power. As power increases, the impact of mobility decreases and the effective density increases. So when you increase the power, obviously the mobility will be decreasing, the impact of mobility decreasing, and the effective density also increases. Okay, so then next is, by default OLSR is used, but specifying a value of 2 for the protocol will cause AODV to be used. Specifying a value of 3 will cause DSDV to be used. So by default OLSR is used, and we'll check this number. Okay, so by default 2 will cause AODV. So AODV, the value number 2, AODV is 2, then 3 will be DSDV. We'll be running with number 3. Then by default OLSR, we'll see that in the source code, we'll see that by default there are 10 source sync data pairs sending UDP data at an application rate of 2 MB per second. So that's what we have seen, 2 MB per seconds. So that is kilobits per second. Sorry, 2 kilobits per second. Then the data is transmitted between the source and the sink. So there are 10 pairs of source sync data pairs. Source destination pairs. 10 in numbers. Totally there are 10 in numbers. Source sync data packets. Okay, so then application data is started at random time between 50 and 51 seconds and continues at the end of the simulation. That's fine. So now the program outputs a few items. So it outputs the source address, timestamp, node ID, and there are some CSV file. It just prepares some CSV file. Anyway, no issues. Let us not bother about it. So we will run through our examples. Okay, so we'll go through that. Okay, now having set these parameters, so some more parameters will be filling it up here by understanding the source code. Okay, so we will just log into. Okay, now we have the source code. So we have include header files. So some of the header files. So in this we can see AODB module. So the header file of AODB protocol. So OLSR protocol, BSDB protocol, and DSR protocol. So for individually all these protocols, the files are included here. As I already pointed out yesterday, all the protocols are already pre-compiled. So you are free to use any protocols available in NS3. So these 4 protocols are being used. So now 2 namespace NS3 and DSR. We have 2 namespace. We use that. So for DSR we have a namespace separately. For NS3 we have a namespace separately. So okay. Now first thing is we have a class. So you know that in C++, the class contains data members and member functions. That's what we have studied in our books. So in C++, the class contains data members and member functions. So we have public, private, and protected. So these are the 3 modes we will be having. So in the public, we have now routing experiment. The name of the class is routing experiment, and this also routing experiment. So this is called as a constructor. So routing experiment is the constructor. So we have a function here. Routing experiment, the constructor is there, and run function. So in the run function, we have number of things, transmission power, and a CSV file name. So the CSV file name what we will be having. So there are 3 parameters for the run function, and we have the command argument vector and argument count and the vector. So we have a double pointer here. So count and the vector. Okay, this is on the public side. So usually functions are public because the functions are encapsulated, and private we have some variables and some private functions also. So in the private function we have packet receive function. So in the packet receive we have IP version 4 address and the pointer to the node and the node number. So node number and the IP version 4 address. Then in the receive packet we have the receive packet receiving from which socket. So that's the receive packet function. Then check throughput. So we are checking the throughput right away inside this function. We will see that also. What is the throughput value? Now here port number. So U int 32T, that means unsigned integer 32 bits. So that's what unsigned U int 32. So the port number, since we have the port number up to a value of 65535, so it is in unsigned 32 bit. Then total number of bytes, then packets received, then CSV file name. So we have a CSV file name, then number of things in integer, and protocol name. So which protocol we are going to use? So we are going to use 4 protocols: AODB, and OLSR. So I'll just write the commenting there so that you can understand in a better way. Then TXP is the transmission power. So this is on a transmission power. That's what the TXP means. Then trace mobility. So it's a boolean. So either it is true or false. So that trace mobility, and this is a protocol number. So it is a number here. So we want to mention a number. So the number could be 0 or 1 or 2 or 3. We'll see whether 0 to 3 or 1 to 4. That we will see. Okay. So that is on the number of protocols. Okay. Now we have a routing experiment. So constructor is called. Constructor is called or initialized, we can say. Initialized or initialized. Okay. Constructor is initialized. So port number 9 we will be used here. So total number of bytes will be 0 bytes. Then packet received will be 0. the CSV file name what we will be getting is Manet routing output.csv. So what I do is I'll just change the value to Manet output. I'll use this way, Manet output VVCE.csv. So to understand that we are doing it for this exercise, so we will put the college name Manet output VVCE.csv file. So this is a file we'll be getting. Then trace mobility false. That means we are not going to trace the mobility. So in what speed move and how it moves, which location it moves, we make it false. So I mean we are initializing now. Whenever we need, we can change it. So M protocol number 2 is for AODV. So AODV is number 2. Already we have seen this here. AODV deals with number 2. The value is 2. Okay. So this thing we have done. Okay. So constructor initialized. So next thing is receiving the packets. So there's a function receive packet, the second function. So print received packet. So it is an inline function. So received packet. So the parameters are socket, packet, and the address. So these are the 3 parameters. So you can see in the beginning we have this routing experiment. So we have here receive packet. So received packet, not this function. So that's the inline function. Just now we are just starting the inline function. So print received packet. So we have a socket, packet, and the sender address. So now here we have a standard output, output stream in object name OSS. So it is a output string as a stream. So we have this OSS. It's an object name. The name of the object is OSS. Now we'll be getting the current time. So simulator now dot get seconds. That's the current time. We'll be getting the current time and node and the ID, node ID. So we'll be getting the current time and the node ID. I'll show you in while I run the example. I'll just show you what does this mean. So OSS redirecting. So this is an output. So the following line will be printed to the terminal. Following line. So what are the parameters to be printed is the current time and the node ID. So these two will be printed. Okay. So now if it is from a sender address, if the INET socket, the internet socket address is the matching type with the sender address, then received one packet from the IP version 4. You will see the IP version 4. So received one packet from which address? So you may be getting something like this. For example, received one packet from 10.1.0.2, something you will be getting. You will be getting a message like this in the terminal. So that means which node receives this packet. Okay. Else received one packet. If it doesn't know the sender address, it will be simply putting a message called as received one packet. Okay. So this is on the received packet. So it is an inline function. So directly it will be printing. Okay. Now receive packet. So how many packets are received? So that is this is a function is already there in the routing experiment. So we have this bytes total equal to bytes total plus bytes total equal to bytes total plus packet get size. So the size of the packet will be added, and that added value is sent to the packet received. Packet received equal to, so it is something like this, n I equal to I plus 1. This is the logic here. The same logic here, packet received equal to packet received plus 1. So that means one counter is incremented. So every time when a packet is received, okay, then it will be printing it this value. Print received packet, it will call the function socket, packet, and sender address. So according to the number of packets, it will be printed there. So we'll see this this output also whenever we do our experiment. We'll see that. Okay. So next thing is routing experiment. We have another function called as check throughput. We have a check throughput function. So what does this function do? So we have KBS, kilobits per second, the variable name KBS, bytes total into 8.0 divided by 1000. So kilobits per second. So first you just convert that into bytes, so 8.0 divided by 1000 is for milliseconds. So it is for milliseconds. So that's how the way we use it. So bytes total initialized to 0, then the CSV file name, and we just print these values. So out, what we print is simulator colon now dot get seconds. So the time will be printed. Along with the time, you will have this KBS, this value will be printed, bytes total. How many packets received will be printed. The number of syncs will be printed. Protocol name will be printed. Transmission power will be printed, and end line. So the complete thing will be printed. So how many parameters are printed? So 1, 2, 3, 4, 5, 6. Totally 6 parameters are printed on the CSV file name. So in CSV file, 6 parameters will be printed. In the following, printed by the following line. So totally 6 parameters will be printed. Okay. So the what are the parameters is the current time, that is get seconds, the KBS, the double value, the bytes value. So this kilobits per second, this value, packets received, number of syncs, protocol name, transmission power. Okay. After that, the next line will be printing it. Okay. So this is called as the throughput. So this is the check throughput. So what is the throughput? We are checking it directly using the function available. Okay. So once this is done, we'll have the next experiment, next function, set up packet receive. So how we set up the packet receive function? So we have a function called as UDP socket factory. So we have so many socket factory here, TCP socket factory also available, and HTTP available. So there are so many source codes available. So in this we have one source code called as UDP socket factory. So this is one of the name that it refers, UDP socket factory. So in this socket factory, we are just setting up the packet receive function as per the IP version 4 address. So each and every node will be having an IP version 4 address. So which node is sending the packet, which node is receiving the packet. So all the data will be transferred via in the transport layer via this UDP socket factory. So that's what this relevant code is available here. Okay. So next thing is command setup. So in the command setup, this is a routing experiment. In the command setup, we have CSV file name, trace mobility, protocol. So protocol you can see 1, 2, 3, 4. It is not 0, 1, 2, 3. It is 1, 2, 3, 4. 1 for OLSR. I'll just write it down now. So protocol OLSR for 1. Then DSR is for 4. So as per this example, we have 1, 2, 3, and 4. So we have these 4 protocols. Okay. So, but what about this? Why we are giving these variable names? I'll just show you these variable names. So we can dynamically, during running the example, we can dynamically modify these variable names. I'll just show you that also. So there are 3 command line variables that we can have control over it. Let's say if I want to dynamically during runtime, if I want to change my protocol to DSDV, I can do that. If I want to change it to OLSR, I can do that. Okay, so that's why we are giving the value called as protocol here. I'll show you that during the running of example. I'll just show you. Right. So next thing is we come to the main function. So in the main function, we have routing experiment, CSV file name, experiment.command setup. So we are getting the output in the CSV file name. So what is the heading of the output is simulation second, receive rate, packet received, number of syncs, routing protocol, and transmission power. So you might have seen that we 6 variables are printed. So what is the heading of the particular variable? So before we generate the values, we have to put the heading in the top, like how we do in the Excel sheet. In the spreadsheet, what we do in the first row will be the title row. After that, we have the we will be filling the values. So what are the titles? These are the titles. So simulation second and receive rate, packet received, number of syncs, routing protocol, transmission power. Okay. So now in this case, how many syncs are there? Number of syncs are how many? Totally there are 10 sync. That's what we have seen, that the source sync parameters are totally 10 number of nodes. We have seen that. And transmission power is 7.5 dBm. So this also we already have mentioned it. So we are declaring here only. So here this is what we call as 7.5 dBm. Okay. So this is the decibel meter. Okay. Then experiments dot run, number of syncs, TXP and CSV file name. That means the 10 nodes and 7.5 and the name of the CSV file name. So that's it's over. The main function is over. So a very simple main function. Now we are going to implement the run function. So this run function is a very bigger function that involves all the parameters of the entire simulation. So we are setting the Wi-Fi parameters, everything. So this is a run function. Okay. So this we will be seeing how the run function performs. Yes. So this one will be performing now. So the run function have three parameters, as we said, that number of sinks, transmission power, and the CSV file name. So these are the three parameters it will be having. So now first thing is enable printing. So packet enable printing. So packet type we want to enable the printing. So that's why we have this packet enable printing. So m sync n syncs equal to n sync. So it is something like m equal to this dot m. So you might have seen in C program C++, we'll be doing this. This dot m equal to m. So something like this we might have seen it. The same way here, these are the class variables. This is the variables allocated in the function. So these are function variables. So m underscore n6 it is declared in the class. So we are equating these three. So m6, txp, and csv file name. Okay. The number of Wi-Fi nodes totally 50 nodes. So we have already seen that. So total number of nodes is 50 numbers. Okay. So we have already seen here. Total it is 50 numbers. Total time is 200 seconds. So 200 seconds is so large time. So we have reduced that to 70 seconds. So let us run the simulation only for 20 seconds. Up to that, your simulation start only by 50. It starts at 50 seconds and ending at 70. So totally 20 seconds simulation will do that. If it is 200 time, if it is 200 seconds, then we have to wait for a longer period of time. So that's why I'll make it to 70 seconds. So now I will change the total time to 70 seconds. I'll just change it here to 70 seconds. Okay. Then we have a rate. At what rate the data is sent. So as we have already seen that 2 MB per second. So 2048 bits per second is 2 kilobits per second. That's what here the rate at which the Wi-Fi nodes works. And the physical layer mode is DSSS rate 711 Mbps. As we are using the IEEE 802.11b. The maximum rate is around 11 Mbps. The speed of rate is 11 Mbps. The TR name, the file name is Manet routing -compare. Okay, so in this we will use Manet routing VVCE. We change the file name as Manet -routing VVCE. So that I will be changing this. So node speed in 20 meters per second and node pass. The node will not be stopping in between. So that's why this 0. Node pass is 0. So protocol name is, the name itself is protocol. Okay, so these are the parameters that set in the run function. So next we'll come to this packet size and data rate. So we have packet size, on off application, and this also on off application rate. So on off means either the full packet size or no packet size. That's what here the 64. The packet size is 64. If no packet size, it will be 0. So 0 or 64. That's what this on off application. Similarly, data rate, it's at a rate. So the rate value here is we have 2 kilobits per second. That is 2048 bits per second. Okay, right. Now next thing is we have a remote station manager, Wi-Fi remote station manager in the non-unicast mode. So non-unicast mode means it is on a multicast mode. So there will be multiple nodes. They can able to get their information. So we have a remote station manager. So that's what here, the station manager. Okay. Now we are creating a node container. Now we are come to the first entity in NS3. NS3 node class. As we have seen in the yesterday session, so we are creating a ad hoc nodes. The variable name is ad hoc nodes. Creating n Wi-Fi. N Wi-Fi is already 50. So creation of 50 nodes. Creation of 50 nodes. So we are creating it. Okay. Now next thing is we are setting the Wi-Fi physical layer standard. So in the Wi-Fi helper we have set standard. We have Wi-Fi PHY standard 802.11b. So we have already set this 802.11b. So accordingly we just use this protocol. In case we want to change it to something else like 802.11n and other stuff, that you can able to do. So additional parameters has to be set for those. Okay, so that's what here. Okay, next thing is physical layer, YANS Wi-Fi. So YANS, as I already told you yesterday, it is YANS means get another network simulator. That's what YANS means. So we have a Wi-Fi PHY, the variable name, and the default set of parameters. Again, I just reminding you, this parameter, if at all if you want to use the communication parameters of it, like transmission power, gain, L factor, frequency, all these things. If you want, if you are from electronics background, communication background, you can think of setting the physical layer parameters. If you are from computer science, you bother only about the networking. So let us use the default set of parameters. Okay. So next thing is channel Wi-Fi channel. So creating a communication path. For that we have propagation delay. So propagation delay is constant speed propagation delay model. So I'll just use that also. So constant speed propagation delay model. So what propagation delay model you are using? The name of the propagation delay model is constant speed propagation delay model. Okay. So that's what we are using. So then add propagation loss. So propagation loss model is Frisch propagation loss model. So there are various loss propagation models. So we have already used Frisch loss model, propagation loss model. So we are already using it. So in case if you want to check other propagation loss model, you can check it. So maybe possibly I'll show you the source code of those also. Okay. Now create a set channel. Now this once you create a channel, this will be applicable for those constant speed propagation delay model and Frisch propagation loss model. If you are from a communication background, you can think of handling these propagation loss models. Okay. Next thing is a Wi-Fi MAC. We are creating a MAC now. Then constant rate Wi-Fi manager. So it is the constant rate means so all the nodes in the network will get the same speed of Wi-Fi network. So it's something like 100 Mbps bandwidth you are getting. So means all the people will be getting 100 Mbps. So in a university, let's say if you take a university, if they are giving internet services for all the students in the university, for all the students they'll give a equal constant rate speed. 4 Mbps bandwidth, 8 Mbps bandwidth for all the students. Similarly, this is what we call as concentrate Wi-Fi manager. Okay. So now this also we can make use of as a parameter. Wi-Fi manager type is concentrate Wi-Fi manager. So now we have the physical layer transmission power start and transmission power end. So from starting to ending, we have only this 7.5 decibel meter. So TXP is a value already been set as 7.5. So starting also will be 7.5 dBm and ending also it will be 7.5 dBm. So there is no change in the transmission power, and the transmission power while starting to end it is always constant. That's what it means. Okay, so now we have the MAC. So MAC, we have different MACs, but now we are going to use ad hoc based MAC. So we have the MAC type is ad hoc Wi-Fi MAC. So the MAC type is ad hoc Wi-Fi MAC. So this is the MAC protocol type that what we are using. So next is then installed on the ad hoc devices. So the net device container install on all the nodes, install this Wi-Fi MAC, ad hoc Wi-Fi MAC. So Wi-Fi PHY, Wi-Fi MAC on the particular ad hoc nodes. So totally 50 nodes. All the 50 nodes are programmed with ad hoc Wi-Fi MAC. So then mobility helper. So because since in the yesterday's example, only 3 nodes are mobile, but here all the 50 nodes they can move. So that's what we need to have a mobility model. So in the mobility model, so what kind of mobility we have? So that have been extended here. So first we have a position allocator. So yesterday you have seen the position allocator is grid based. Now here it is random rectangle position allocator. So we have a position allocator called as a random rectangle position allocator. So I use this also. Position allocator. So a random rectangle position allocator. So this is what in one of the parameters of the next thing is, so in this x and y, we have already mentioned the x and y here. X is 300 meters, so we can see that minimum is 0, maximum 300. Y is minimum 0, maximum is 1500. So minimum is 0.0 here. That's what we have uniform random variable. So as uniform random variable, the value will be set as 0 to 300 or 0 to 1500. So this is what a random rectangle position allocator. So rectangle position allocator will be on a x 300, and y will be 1500. So that's what random rectangle position allocator. Okay. So then assigning the streams for those. So for the position allocator, so allocate the position values to the streaming. So for streaming all the information in the particular area 300 or 1500, allocate the assigning the streams for that. Okay. So now the node speed. So how the node moves. So the node minimum 0.0, maximum is node speed. The node speed is already we have given as 20 meters per second. So starting from 0 to 20 meters per second, the nodes will move. Okay, so all the nodes may not move at a speed of 20 meters per second. It is on a random. That's what uniform random variable. So some node will be moving at 1 meter per second, some will be at 5 meter per second, 7.8 meters per second, some will be moving at 20 meters per second. So starting minimum is 0, maximum is 20 meters per second. Then there is no pass time. So pass time we have given 0. Pass time means there is no stopping in between. So that's how the pause is 0. So constant 0. So it is only constant random variable. It's only the value is 0. Okay. Now the mobility model. The mobility model is random waypoint mobility model. Already we have mentioned here. The mobility model in the beginning we have mentioned as a random waypoint mobility model. Okay. So in this mobility model we have three things. So one is speed of the node. Next thing is pass time, and next is position allocator. So we have speed, position allocator, and pass time. All the three are available here. So speed on 20 meters per second maximum, pass time is 0, and position allocator we already have a random rectangle position allocator. So that's what we have this random waypoint mobility model. So these things are fine. So after each and everything, we are streaming the data, so that's why we are using the streaming index here. Now we are coming to the protocols. So here we come to the protocols. So this is the protocol. So in these protocols, what are the different protocols list available? So we have a first class called as AODV helper. Object name is AODV. Then OLSR helper. The object name is OLSR. DSDV helper. The object name is DSDV helper. And DSR helper. The object name is DSR. And DSR have a namespace. So it is having a main helper also. So we have a main helper as well as the DSR helper. Then we have a IPv4 routing helper list, internet stack helper, internet. Okay. Now switch M protocol. So we have a switch case function. So this protocol will value take from M protocol will be this value can take 1, 2, 3, 4. You can see here the value 1 is for OLSR. The value 2 is for AODV. The value 3 is for DSDV. The value 4 is for DSR. Okay, so we have these 4 numbers, 4 protocols. Then beyond some number 5, 6, 7, 8, so it will be no such protocol. Okay. Then if M protocol less than 4, so we have internet set routing helper list and internet.install ad hoc nodes. So less than 4, that means except DSR, all the other protocols we can just using the routing helper, and we can install the internet on the ad hoc nodes. But in DSR protocol, that's a slightly different thing. So internet.install ad hoc nodes, then you have to install DSR main. So DSR main.install DSR ad hoc nodes. So you have to install dynamic source routing protocol into ad hoc nodes. If it is 4, if it is 1, 2, or 3, if it is OLSR, DSDV, or AODV, the value is simply these 2 lines. If it is DSR, you have to include this extra line. So that's how this logic here. Then assigning IP addresses. So IP addresses, you can see here the address ad hoc is 10.1.1.0 255 255 255 is a masking value. So we will change it to our own number 100 point, sorry, 200.10.24. This is what we have done it yesterday. The same number we will be using it today also. So then we have on what basis the packets are transmitted. It is on UDP socket factory. So constant random variable and constant random variable. On time is 1 and off time is 0. So that's what here on time 1.0 the constant and off time is 0.0 is the constant. As per this, we have just set it. And then we have a option here. If I equal to 0, I less than number of things. So we have to just, we have creating the nodes, we have created the nodes, we have created the protocols. Now between the 10 pairs of source and the sync destination, we have to exchange the packets based on UDP socket factory. So for that, the number of things is totally 10. So we are just initializing the packet receive function. So set up packet receive, then remote address, then attribute is remote, then as per the uniform random variable, so each and every node. So ad hoc nodes are get of I plus n6. That means get of I means 0 plus 10, then 1 plus 10, 2 plus 10, like that. So each and every node will be exchanged, exchange the packet between the particular nodes. So that is application container. So temp dot start. So starting is 100 to 1.101, but our total time is 70 seconds. So we'll start at 50. So 50 to 51. So our starting time will be somewhere from 50 to 51. So it will be starting, and stop time will be total time. It is up to 70. So it will be stopped at 70. So it will be stopped at 70. So start time will be 50 to 51 and stop time will be at 70 seconds. Okay. Now the value will be printed in the SS value. So a number of Wi-Fi nodes, node speed, node pass and rate will be printed in each and every value. Okay. Now we can enable the ASCII. So as we have seen yesterday, ASCII trace helper, ASCII. So we enable the ASCII value. Then mobility helper, enable ASCII all. So for the mobility, we generate a file called as trname.mob, MOB. That is a mobility factor for the trace file. So this what here we have the ASCII trace helper. Then we have the flow monitor also. Maybe I'll just show you the flow monitor after the first simulation run. I'll be showing you with that. Check throughput, then simulator stop, simulator run, and simulator destroy. Okay. So that's all on the explanation of the source code. So please see that the explanation takes almost 1 hour. The time is 3 o'clock in Indian Standard Time. So just it took 1 hour for explaining the complete source code of 400 lines. Okay. So now we'll be running the basic simulation of it. Okay. Now to run. Listen, now we'll see. First thing is open the terminal. First you just use the CD enter. Then next is CD hyphen ns hyphen all in one hyphen 3.31 slash ns hyphen 3.31. Okay. So then dot slash waf double hyphen run slash manet hyphen routing hyphen compare. So no dot cc extension. So that will be no dot cc extension. Okay. So we'll be running it now. will be running it now. Okay. So you can see up to 70 time units. So 69.925 time units. The starting here somewhere around 50.5989, because we have mentioned as the starting time is somewhere between 50 to 51. And now we can see 9 packets have been received, 1 packet. So there's node number 9 received 1 packet from this number IP address. So likewise we have this value. So we have time unit and we have this. So I'll just show you in the source code what does it mean. You can see here this is what we are seeing. So received 1 packet from. So this is what we have seen, and what value we are printing here is so node ID. So we are printing the time unit, that is the time. So that is 50 to 70. This is the time we are printing. Then the get ID, node ID, and from which node it is receiving the packet. So 10.1.0. But in this case, what we are getting is 200.10.24.20. So this is what we are just getting it here. Okay. So now we'll be seeing our files. Delete all the generator files what I did run it yesterday. Okay, now it is free. Now I'll run the example again. Okay, so even for 20 seconds it takes time. Now you can see we got an output, these two output .csv file and Manet routing VVCE.mob. So one is for mobility, another is a .csv file. So we are getting this two output file. Okay, I'll open this file. So Manet routing. This is a mobility file. So in the mobility file, what is each node is doing, and what velocity it moves, on what location it goes. So that's what here for the entire simulation. Okay. So now equal to 0.01. So 0 seconds we don't bother, because our simulation starts somewhere at this nanoseconds. So this nanosecond means milli micro. So 4.6. So 4.6 seconds. What happens? Node number 7 to this position and velocity at this, and this 4.6 to this time. This velocity is 17.146 and this value. So this is the way the mob file got generated. So this is a mobility file. Okay, so this is on WAN and routing. Now another file we got is mobility output PVC. So this is the output file we got. Okay, so this output file you can see simulation second and 0, 1 2 3 like that. Receive rate, it is 0, again 0. Packet received, again 0. Number of sinks is totally 10 number of sinks. The routing protocol is AODV, and final thing is transmission power is 7.5. Okay, so that's what we are getting it. In this example, you can see after 50 time units, so totally and see here at 1.024 we are getting some results here. 5.63 to 7.68 like that, we are getting some results over here. So at time unit 51. So from 51 onwards, we are getting some values. 51 to 69 because our simulation starts at 50, ending at 70. So 50 to 70, we are getting some results. Okay. So this is what happened in this file. Anyway, we'll see some more details and come. Okay, now what I do is I'll go with implementation of NetAnim. So implementation of NetAnim. So what I do is first include ns3 slash netanim hyphen module dot h. Then animation interface anim I can use manet dot xml. Manet VVCE animation. I can use this way. This is the name of the file. I can use it. Okay. So these two things I need to implement in my Manet example. So I'll go to the header file area. So in the header file, first I'll write like this: hash include ns3 slash netanim hyphen module dot h. This we have done it. Then go to the end of the source code here somewhere. Animation interface anim, then Manet VVCE animation dot xml. Okay. So this example I will be getting the XML file for running the animation. Okay. So okay, run the file. Again I will be running this file. Yes, I'm running. So again I need to wait for some 20 seconds or so because we are having the simulation of 20 seconds. So I'll be waiting. Okay, so I have done this example. So now I'll be checking the XML file. So I got the VVC animation.xml file. So Manet VVCE animation.xml file, I just got it. So now what I do is to run NetAnim. That's it. So CDNS all in one. I'll go here. CD NetAnim hyphen 3.108. Okay, then dot slash NetAnim. Once I do this, I got the network animation file. So in this network animation, I'll select the animation file. So now you can see that you might got some values here. So this is a location node ID and just disabling the node ID and making the nodes to be size bigger. So now we can see this is we called as 300 cross 1500. So this is a network animation 300 cross 1500. Okay. So I'll run the simulation. We can see that how the simulation runs. how the nodes move themselves. Only after 50 seconds only we have our simulation running. So after 50 you just enable it. So I'll make it faster now, because I made the nodes to move 120 meters per second maximum. Still it is 27 seconds. You can see here. We'll wait. Okay, now 46, 47, 48, 49, 50. Now you can see from 50 onwards, you can see there are packet exchange. See, the packets are moving here and there. So maybe I'll just make it slowly here. So because of packet exchange, the simulation also goes slow here. So you can see here the simulation also. Now it is going slow. Though by running the fast simulation, it goes slow because now there is exchange of packet going on. Okay, so now we can read the statistics of the nodes. Then you can see the packet structure also. So how the packet structure to flow from each and every nodes. So this is on the animation side. So you can check whether how really your animation is working. So from source to destination, the packets are moving. Okay, so this is on the animation side. Anyway, I'll just stop it here so that we'll see the other results. Okay, so this is on the animation side. So next thing is we will plot some comparisons between multiple protocols. This we will do some comparison. So for that, what we do is, so in the source code here, um, so the main function. So we have this. We have these three parameters. So CSV file name, trace mobility, and protocol. So let us forget about the trace mobility. So the CSV file name, we can able to change the CSV file name, and we can able to change the protocol as well. Okay. So this I can able to supply directly through the runtime. So we can able to do it through the runtime. Okay. So now what I do is, first I will collect four files. The files namely are AODB, OLSR, DSDB, and DSR. I will collect these four files. Okay. So we'll see these four file names. How we can able to do that? We'll check it. Okay. So this will take a little bit of time. Please listen to this carefully so that you can easily understand how we can able to process the results. I'll just copy this value. So CSV file name. Okay. Now to run this comparison, first we have to run the file. We have to run the file for 4 times. Each time for one protocol. Okay. So the command is /waf double hyphen run And can you see double quotes here? Scratch slash Manet hyphen routing. Sorry, I have Manet hyphen routing hyphen compare. Then space double hyphen CSV file name equal to. Now I am getting AODV. Okay, so AODV space double hyphen protocol equal to. So in this protocol equal to what? So 1 means OLSR, 2 means AODV, 3 means TSV, 4 means DSR. I will go with number 1 now. So let me use OLSR here. OLSR dot CSV. I think file name alone is enough. So anyhow, I'll just check it here. So OLSR dot CSV I need to give, or only OLSR is enough. Then protocol equal to 1. And I need to run this. So I'll just run this command. So this is we call the command line argument. So CSV file name equal to this, protocol equal to this. Now I'll just running this here. So in NS 3.31. Okay, we'll check it now. So I need to get a file in CSV file name called as OLSR. We'll check it whether we are getting it or not. So we have to run the protocol for 4 times. Run this example for 4 times. Okay, so now we can see this is on OLSR. Okay, now we can see a file called as. So we got a file called as OLSR. Okay, so we got a file. Anyway, no issues. So I'll just clear it. Now second time when I run it, use the same thing. Now protocol 2, use the file name called as AODV. Okay, so AODV. Protocol 2 and it is AODV. So I'm just using AODV for the second sector. So please remember, I am just doing a complete project now. So if it is your PG student, I am just doing a PG project now, just in 3 hours. Just in 3 hours, I am just completing a PG project. So I am just explaining the source code, now running the example, now comparing the results and plotting a characteristics. So I'm just doing it. Now check LS. So we have AODV also. We have a file called as AODV got created. Okay. So next thing is, again we have this protocol equal to 3. Instead of OLSR, we'll be having DSDV. And we'll get the file name called as DSDV. I'm just running it. Every time, the main challenge is every time I need to wait for 20 seconds to get completed each simulation. Okay. So you are experiencing a live project demonstration and live project completion with all the results, everything. So we are seeing it now. Yeah, that I have completed. Next thing is protocol number 4 and DSR. How it is running. I think DSR is slowly running. Maybe due to the caching or other thing, we may feel okay. Okay, so now we just see the files. So we got 4 files: AODV, DSR, OLSR, and DSTV. All the 4 files we got on the CSV file. The first part of the file we have completed. Now we'll just go inside. I'll open all the files. Let's see what is the content of it. That's 3.31. So I'll just open AODV, DSTV, DSR, OLSR. All the 4 files. I am just opening it. So in all the 4 files, we got this data. Okay. So now I want to compare all the 4 file data. I want to compare. So totally you can see the first column is common in all the 4 files. The first column is common. So OLSR, DSR, DSDB, you can see that there is a DSDB protocol, this is a AODB protocol, and here the DSR protocol, and here is the OLSR protocol. Okay, now you can see in all the files the first column is common. First column means this 0 1 2 3, this column is common. The last value is 69. Okay, I want to take the x-axis as the simulation seconds. I want to take the x-axis as a simulation second. I want to plot, and the third value 1 2 3 4, fourth column is also common. 10 is number of sinks, number of destination nodes. Then fifth column AODB is the protocol name, and last column is also common. So we don't need these values. Okay, now I want to read this 4 files and I want to plot a graph. Okay, so now I'll introduce one more tool called as GNU plot. So GNU plot is very powerful. You can refer one of my video on GNU plot in my YouTube channel. So how can you plot multiple files with the help of a GNU plot? So you will be using Excel sheet for this. So how can you do Excel sheet? So copy paste all these 4 data in a 4 different file, and you want to compare the common result. So GNU plot can be easily handle this. We'll see how it can be done. Okay. So first editing here is what I do is delete the first line, the top line, because we need only numbers. We don't need commas, we need only numbers. We don't need commas also. We have to remove commas also in the file. So first thing is I delete that thing. So I am going to plot characteristic receive rate and packet received. I want to plot these two. So first what I do is in this I am going to plot these two things. So results to be plotted now. Two graphs to be printed. Oh, the first graph will be simulation time versus receive rate, and the second will be simulation time versus packets received. So I am just plotting these two. So now editing the file. So first they delete the first column. Okay, save it. Then delete it. OLSR also delete it. The first column we delete it. Okay. Now it is done. Now I'll just do that. We have generated 4 files, namely AODB, DSDB, DSR, OLSR. Delete the first 4 lines. Delete the first line in all the 4 files. We are going to plot using GNU plot for the above two graphs. Okay, so we are going to plot using GNU plot for the above two graphs. So delete the first line in all the 4 files. So first I deleted, and replace comma with blank space. Blank space. So replace comma with a blank space. So how can you do this? So go to this file, Control F, sorry, Control H, comma, and replace with a blank space. Give a blank space. So don't give as it is, else everything will be replaced. Okay, blank space you give and replace all. Now you can see the comma is removed. See, everywhere the comma is removed. Okay, so save it. Then similarly go to DSDB, Control H, comma, then comma here, replace all. Okay, save it. Then DSR, Control H, replace all, save it. Then OLSR, Control H, replace all, save it. So all the commas are removed. So now we have first column, second column, third column, 4, 5, 6. So among that we need one, column 2, and column 3. Okay. So column 1, column 2, and column 3. Okay. So now we are going to write the GNU plot script. Now all the commas are removed, and we are going to plot the graph using GNU plot. So this is what the GNU plot. The name of the GNU plot code is GNU code.plt. So I'm going to create a code name called as GNU code.plot plt. I'm going to create a file. So control S GNU code.plt. I'm going to save it in the same folder in NS 3.31. So save the file where all the 4 data files are available. We'll say ODB. So in this case, it is in this folder. I'm going to create this file. Okay. So now I'll just create this. Now first thing is set terminal. I'm creating using PDF. So I'm going to create this GNU plot file in a PDF file. So set terminal PDF. Then set output. The name of the file is receive rate. Receive.pdf. I'm going to get 2 files. So one file is on set output receive.pdf. Then set title is receive rate. SS time. The time versus receive rate. Title of the graph. Okay. So then set X label. X label in simulation time in seconds. Unit is must. Then set Y label. Y label here is receive rate. Rate is not having any unit, so we'll use this receive rate array. Okay. Then plot. Now we have a command plot. First thing is AODB using 1:2. Please remember, first plot AODB. First I am taking the AODB file because the file doesn't have any extension. So we might have created using AODB.csv, but we have created without any extension. So give the same name here. Plot AODB using 1:2 with lines points. So 1:2 means first column and the second column. So we are going to plot first and the second column in all the 4 files. Okay. So plot AODB. The name of the file is AODB using 1:2 with the lines points. So with the lines points and title. So what is the legend for that file is I am going to use AODB. So to differentiate, I am using small AODB here. Okay. Then comma. Then BSDB using 1:2 with lines points title DSDB. This is for the second file DSDB. Now third file using a while SR using 1:2. In all the files, I am going to use the first column and the second column. In all the files, so using 1:2 with lines points title OLSR small letter OLSR, then comma DSR using 1:2 with lines points title DSR. So I have done my first graph. Okay. So set terminal PDF is the name of the PDF file that I am going to use, receive.pdf, and the title of the graph simulation time. Receive rate is x-axis and y-axis. We have given the name and the command. A very simple example for to run. Okay. Now to run this command, I'll just copy this and paste it here. To run the above file, Go to the terminal and give the command gnu plot space gnu code.plt and check the folder for the PDF file and check the folder for the PDF file generated. Okay, so I will be running the command now. So this command here is gnu plot. So you might have installed gnu earlier. So the command to install is sudo apt install gnu plot. This is a command to install. I have already installed, so no issues in that. In case you have not installed, it will be installed. Now gnu plot space gnu code.plt. So this is a command to run. So once you run it, so if you do not have any errors in the file, you won't get any messages here. So then you can go to downloads, sorry, home, NS all-in-one 3.31, then NS 3.31. You might have got a PDF file. So the PDF file name is receive.pdf. You can see that there's a file. So once you open this file, this is the receive rate. So you can see now here up to 0 to 50 this graph. In 0 to 50 there was no simulation happening because our simulation starts only at 50 seconds. So after 50 seconds you can see the green color is DSDV. This is a receive rate. Among the DSR having the receive rate of high receive rate. After DSR we have AODV. So then we have OLSR. Then finally we have DSDV. So DSDV is in the bottommost thing, and others are in the DSR in the first, in the top. So DSR performs well in the receive rate and compared to the other three protocols. So AODV, so on an average, it is performing better than OLSR and DSDV, but somewhat less than compared to DSR protocol. Okay. Now you can see this graph seems to be small boxes there. So I have given only lines and points. So in the graph, so what I do is I'll go back here. Instead of lines points, I will change it to points alone. So you can just give only points. And give only points. Let us check with the multiple options. We can give only points here. So we have to give all the four things here. Here also we have one. Okay, so points. Then again we'll run the example. Now you can see this is the points, only points. No lines are there, it's just only points. So in this case, we can get to know about the points. Now let me go to, instead of points, I'll make it as lines, points to lines. Replace all. Okay, now we'll check it again, saved it, I'll run it again. Go to the file here. Now we can see only lines. So this seems to be a better option here there because up to 0 to 50 nothing is there, but beyond that you have these values. So 50 to 70 you got the results. Now we can clearly understand that DSR having good receive rate when compared to the other three protocols. But you can see the DSTV protocol only after 60 only the receive rate is there. Up to 50 to 60 also there was no receive rate. So hope you understand how we have done it. And you can see this is a title. So this is a title of the graph is time versus receive rate, and x-axis on simulation time versus seconds, and y-axis on receive rate. This we have checking, and these are the legends: AODV, DSTV, DSR, and OLSR. So GNU plot is very powerful. So most of the graphs you can able to plot using GNU plot in most of your research work. Okay. So now we have one more graph also we can able to plot it here. First what I do is Control A, Control B, and Control V. So we will do one more graph also. In this case we are using packets received. The name of the file is packet received. This is the third column. So first column, second column, we have already done it. Third column. So here time versus packet received. So here in the x-axis, y-axis is packet received. 1:2, we have 1:3. 1:3 is for third column, first column and the third column. Yes. So now we'll run the example again. Same thing again. Now we'll be generating two graphs in the same folder. So receive rate is here, and we have the packet received. Okay, so same way. So packet received and receive rate doesn't have any difference because the values resemble the same in the as per the data file. The values resembles the same. So that means the value resembles the same. So you can see here 2.0, here it is 4. So 3.5, it is 7. So across all the 4 protocols, the value is just proportion to what value in the packet received column of all the individual protocols. So we have plotted two graphs, two characteristics, one with this. Okay. So in case if you don't want 0 to 50, then we can give the range of x range 50 to 70. So maybe we'll try that. Set x range 50 to 70. Yeah. So now we can see x range is 50 to 70 means, so it starts from 50 to 70. So this graph seems to be a better option. So first graph is, so this is on packet received and receive rate, that is also same 50 to 70. Okay. So 10 to 50 is nothing is there. So if you don't want to print, so let us not bother. So we'll start only with 50 to 70. So the column here is x range. So x range 50 colon 70 in the square bracket. So once it is done, so our command is will taken. Okay. So this is on the plotting the characteristics using GNU plot. So this also is just included here. So to run the GNU plot code, we have the command, this command. So you can refer my video. YouTube channel for more details on GNU plot for graphs and plots. So this way you can try out these characteristics. Okay. So what we have done now so far is, so we have done one thing is net anim, number 2 is the CSV file generation for receive rate and packet received. This we have done. Okay. So animation we have seen. Third thing we'll go with flow monitor. Sorry, flow monitor. This will be doing the flow monitor. Okay. So flow monitor is very powerful. We can able to find the packet loss, then packet or drop, and other informations relevant to packets. So how to enable flow monitor? So the logic is very simple. We'll go to the code. Already this example has a flow monitor. So in this code here, we have these 3 lines. See, remove these lines. Already the commented lines, we'll remove this. Here you can remove this. So this is what the flow mon. Okay. But here we have the flowman. The file name is called as .flowman. This is the name of the file name. So that we have to parse it. Parse means we have to read this file as per the need. So this is the flowman file. So we have a tr name here. So first find out what is this tr name. Control F. Control V. So tr name is, so we get the file name like this, Manet routing VVCE. This is the flow monitor file. Okay. So this is the name of the file. In all the examples, we'll get the same Manet routing VVCE. So we'll get this .flowman we'll get. Okay. Right. Now I'll run this example. In this, what I do is I run simply WAF. So in this case, we are getting only AODB protocol. I'll be running it now. AODB protocol. Okay, we are getting some error. So first time we are encoding some error. The reason is okay. Oh, we have to have the header file. Sorry. Okay, I'll go and implement the header file. So I need to include the header file. Hash include ns3 slash flow hyphen monitor dot h, then hash include flow hyphen monitor hyphen helper dot h. These two header files we have to implement. So flow hyphen monitor dot h, flow hyphen monitor helper dot h. Okay. So I will run it. I think it's running now. Yeah. So by default, as we have seen, by default it is AODB is running. In case we want to change it, then the same way, double hyphen CSV file name, double hyphen protocol, like that we have to change the protocol and the name of the CSV file. But now we get a flowmon file that is for AODB protocol. So we are getting a flow monitor file for AODB protocol. Okay. So we got a file called as flowmon. See that? Manet routing WWC. So when we will open this file, so this is how the way the XML file looks like. So total numbers you can see. So if you see, there are 1,393 lines. Okay. So this only we have to plot it, or we have to parse this. So XML parsing is one there. So we can plot this. So using some tools, we have to plot it. Okay. So this is the flow monitor file for the AODB protocol. Because first time we are running it, it's AODB protocol. So anyway, there is a parts are already available in NS3 itself. CD SRC, CD flow monitor, CD examples. So here we have a file called as flowmon parse results.py. So we have a Python script. Okay. So flowmon parse results.py. So we have a file. So first we will copy this file and put it in the ns3.31 folder. Okay. So cp flowmon, we'll put it in ns3.31. So we have copied it. So now we have a file called as flowmon parse results file. Okay. So we got this file. So now to run this file, what we do is, and I'll just mention it here. Uh, so we have the following enter flow monitor. So what we do is these three lines. following line to be included after the simulator colon run function. Find three lines to be included before the simulator run function. So parse the dot flowman file. NS3 has a file called in the folder. Okay, so this is the longest one. Anyway, I'll just share this file to you so that you can later on you can understand also. So I need to do this time. So what I do here is Python 3 flowman dot parse dot results, then manet manet hyphen routing flowman. So reading XML file. Just wait, I'll just check it. I'm installing Python. For Python 3, I think it is struggling because print have a parenthesis, but Python 2.7 doesn't have it. So anyway, just installing Python 2. Yes. So actually, this is the flow ID. So you can see packet flow ID. It is just printing. Okay. So what I did is I install Python. Sorry. So I install Python. Use Python. Then to install Python, you can use this command. That's it. So the flowman is fine. So in case we want to rename, You can rename this also. So to rename, what I can do is this line, copy this line, copy this. We can use move XML. So this is the way you can change it to XML file. Now we can see here the Python flow here is the flow ID. So the packet loss ratio at some point of time it is 0, and for some mean delay is 6.47. So transmission bit rate, receiving bit rate. For some it is none. Mean delay is none. Okay, for some bit rate, for some flow rate, we have a bit rate of 1.07. For some bit rate, we have 89.9. So likewise, we have it. So if you want to edit, you can edit the parse file. So you can edit the parse file, make the average workflow. Maybe I'll just show you that also. If possible, I'll just do it. So in the Python flow here, so packet loss ratio is coming like this for each and every bit, and here flow bit rate is none. So flow bitrate is none, then print L times in bitrate into this delay mean packet loss ratio. I'll just check it. I have some time back I have done it. Flowman parts results.py. Yeah. So I just got it here. I'll just download this file. Okay, so I have just implemented this file some time back to find the average end-to-end delay, and you can see this is the average end-to-end delay for this example. Okay, so this is on AODV protocol. So this is the end-to-end delay factor for the particular AODV protocol. So using Flowman. So I have just modified the flow monitor parse file according to my need, and 0.0239 seconds. Okay, I'll just tell you this also how I can able to do. So This is the source code here. So everywhere we have a mean delay. So mean delay has been printed. So I have taken average end-to-end delay by flow dot mean delay mean divided by flow dot flow ID. So number of flow I just taken it for average end-to-end delay. Okay, so this is the average end-to-end delay that I am printing it here. So in this case, this average delay I just calculate for each and every network. So as of now, this is for AODB. So what I do here is I'll create one more file here. First thing is, sorry, control T. I'll create it. The file name is delay. Capital letter I can use delay. I use delay. So first value here is one is OLSR, number 2 is AODV, 3 is DSTV, 4 is DSR. Now for 3 is 0.239. So I think it is 0.0239. So this is a delay for AODV protocol. Number 1 is for OLSR. So what I do for OLSR is I need to run the protocol again. So what I do here is WAF. I just go through WAF now. So WAF in this Manet routing compare. At the end, I'll come back here, hyphen protocol equal to 1. So I'll run only protocol equal to 1. So now whatever file I am just getting, I'll be getting it for the flow monitor file for OLSR now, because protocol 1 is for OLSR, 2 is for AODB. Now I plot that character 6 also. Okay, so now this for OLSR. Okay, so now I'll be running the same file again, flow monitor. So flow ID is I think very limited. I think so totally there are only flow ID is one file like this. So the flow ID is very small. So that's why this OLSR is not printing. Anyway, just we'll go with one more thing called as protocol P. Okay, so now again I'll run it. So this is 67.07 is the delay. So in DSTV. So this is a delay here. And one more thing is DSR. I need to run DSR protocol number 4. So again this also have something issue reading XML file. The reason being so DSR doesn't get any flow monitor. That's the reason. So protocol 44. I will run one more time. Let's see. Okay, so I think no information is there for this. Then finally, protocol number 2, that is AODV. One more time, I will just run it. So for each and every simulation, we have to wait for some number of time. But the actual Manet routing example, it will be given for 200 seconds. So 200 seconds means every simulation will be running for around 5 to 7 minutes. So that's why I just reduce the time to 70 seconds. Maybe if I prolong the number of seconds, simulation seconds, then I may be getting some random flow, the packet flow here. Anyway, this is an AODV. I'll run this command. So this is the delay, the same delay I'm getting 0.039. So now this is the delay factor I'm just getting in here. So protocol number 2 and 3 only. So 1 and 4, the for OLSR and for DSR I'm not getting. So I'm just getting only for these two. So you can see the end-to-end delay. It is very good for AODV protocol, whereas it is very high for this DSR protocol. Sorry, DSDB protocol. But again, this we cannot make it. We cannot make it happy because the packet flow also includes 0 to 50 seconds. So 0 to 50 seconds, it is ideal. So only from 50 to 70 only we have to take into account. So 0 to 50 anyhow there are some packet flow there. So this packet flow we will not take it into account. So because of this, no packet flow, considerable packet flow. So that means we are using the average flow ID. So average flow ID means in the numerator, denominator we have this. So denominator we have this. So in that case, we cannot claim it as a perfect end-to-end delay. But still, we have some got the good results in AODV and not so good in DSTV protocol. Okay. So if you want to plot this also, we can able to plot. So this can be easily plotted using if you want GNA plot, you can directly use it here directly. So what you can do is, let's say if you want to use in the same PDF file, if you want to use, then you can use output, leave it as it is. So you can use set title protocol versus delay. So this you can use. The next label is protocol. So that means 2 for AODV and the 3 for DSTV. This you can use. And the Y label is N to N delay in seconds. So we have only two values, so we'll delete all other things. So we have this. So we have DSDV here. The file name is delay. So delay using 1:2. Similarly here delay using 1:2. Only one is enough. So we are not putting two files. Only one file is enough. That's enough. Okay. So now I'll just save this file and delete all other data containing only these two. So now we can delay is the uppercase letters. All finds y value undefined. Okay, sorry, X range. We don't need X range here because it's common. Now go to the folder. You got packet received and you got delay also. So delay is the only thing you got. So for 2 it is very less, and for 3 it is very high. So this is delay for AODV and DSTV. So for 2 it is AODV, and for 3 it is DSTV. So even you can plan for histogram also, but anyhow I just plotted without any histogram. So if you want to know about histogram, you can just refer my channel. Okay. So a very long result here in this example. Okay, so I'll just compare it here now what we have done. So the third thing what we have done here is we have done these 3 things. So in this example, so net anim for animation, CSV generation for receive rate and packet received, the flow monitor, packet loss, packet drop, and other information relevant to packet analysis. So this thing we have just done it using flow monitor, but you can refer other tools for flow monitors. This also you can try other tools also for parsing flow monitor files. Check my channel. I have some other tool to plot packet loss, drop, and delivery ratio. Okay. So that's all for this Manet routing compare. So such a very long file and very long processing of results, and even we can use ASCII tracing also. So there is an option called as ASCII tracing helper. So this is also possible here. So how can we process the ASCII value here? Yesterday I was showed you. So this also you can able to try. So with this we can able to do multiple protocols and everything. So now I'll be showing you the source code of where all the source code relies. Sir, I want to do a project. So how can I start? Where can I start? So where can I start when I want to do my project in NS3? Okay. So this is where my challenge. So how I can start? Okay. So this is one famous question that everyone might be asking. Okay. Now so this is a folder where we have all the sources available here, SRC. This is the source where you have the complete source code of all the protocols. Understand those and perform the examples and run it and understand it. Okay, so in this following folder, you have all the source codes available. So you understand the source codes and run the examples and understand it. Okay, so what we do here is I'll just show you that here this is a place where we have the source code. So you can see that. So there are famous source codes available here. So these are the source codes. So one example here is AODV, then LTE, there is a 4G LTE network, mesh networks, mobility, net anim network, then propagation. So I was telling you the propagation models. So this propagation and Wi-Fi. I'll just show you the Wi-Fi. Whatever we have done it so far, I'll be showing you what is this Wi-Fi contains. So CD Wi-Fi. Then in this folder we have bindings. We have document, we have examples, we have helper classes, we have model classes, we have test classes. So in the examples, I'll be showing the examples. So the examples you can see there are different Wi-Fi manager example, Wi-Fi physical configuration, physical layer test, then trans example, this thing. Now I'll go to the source CD models. So in the model you can see what are the different Wi-Fi models available. See that all the source codes are available. Okay, so now we can see we have Wi-Fi manager. So ARF CD Wi-Fi manager, ARF Wi-Fi manager, ad hoc Wi-Fi Mac. Then this ad hoc Wi-Fi Mac we were using. So gedit ad hoc Wi-Fi Mac.cc. So you can see here. This is the type ID we were using. NS3 ad hoc Wi-Fi Mac. This is the type ID we were using inside our source code. Okay. So in case if you want to do something on the Mac Wi-Fi Mac, then you have to understand this file. So how this file is written. So please remember everywhere there is a documentation there. There is some commenting there, so that you can understand the comments well by reading the comments. Okay. So nobody will teach you. Apart from that, NS3 have a perfect documentation. They have a PDF of 1,000 pages documents. So relevant to your area, you can read those documents and you can make understand that. Okay. So this is one. Then you can see YANS Wi-Fi PHY, YANS Wi-Fi channel, then YANS error rate, then Wi-Fi remote station manager. This also we have seen today. Wi-Fi remote station manager. So then we have Wi-Fi physical layer details, Wi-Fi mode, Wi-Fi MAC, then Wi-Fi acknowledgement policy, Wi-Fi configuration, stationed Wi-Fi. Yesterday we have seen something Spectrum Wi-Fi. So RRAA Wi-Fi manager, RRPAA Wi-Fi manager. So these things are there. Okay, so this is on the Wi-Fi. Now I will go to another source called as mobility. So this also we have seen today. In the mobility, we'll go to models. So in the model here, you can see what are the different mobility models. So constant acceleration mobility model, this is one. Then constant position mobility model, what we have seen today. Then Gauss Markov mobility model, this one is there. Gauss Markov means this is one of the mobility model for flying ad hoc networks. If you want to experiment the drones or the unmanned aerial vehicles, then you can use this Gauss Markov mobility model. So this is one of the thing. The particular nodes are flying in the air. That means it is having a 3-dimension, X, Y, and Z, all the 3 dimensions. Then we have geographic positions. Then we have hierarchical mobility models. Then we have position allocators, random direction 2D mobility model, random walk, random waypoint. So today we have seen random waypoint mobility model. Okay, now I'll be showing you that also. Edit random waypoint. So if you see that this is a random waypoint mobility model. So this is what we are using. So what are the different attributes? You can see mobility is one attribute, speed is one attribute, then pass time is one attribute, and the constant random variable is one attribute. Then we have position allocator is one. So likewise for each and everything there are formulas. So if you want to change the formula also, you can change it. So you can have your own mobility model also to handle your own networking. So this way you can able to change the formula here, okay, in this file. So this is where you can use the mobility models. Okay, so this one, and in this example we have seen something called as propagation, the Frisch propagation loss model. So like this. So I'll just show you that also model. Now you can see here last model. We have seen propagation model here. So you can see propagation loss model, propagation delay model, Okumura Hata propagation loss model, Kun 2600, JX propagation loss model. So these are all constant propagation loss model. So we have so many propagation loss model available in this propagation folder. So if you are from electronics background, if you want to try out something on the mobility model, propagation delay model, propagation loss model, you can refer this folder. Okay. So this is one place where you can do things. And if you see something on internet and internet apps, LRWPAN is low data rate wireless personal area network. It is for sensor networks. So if you want to use something on sensor networks, you can plan it at this location. So LRWPAN. So if you want software defined networking, you can try out in OpenFlow, software defined networks. So you can use this OpenFlow. If you want a wave, so wave is one of the beautiful model here. So wireless access for vehicular environment. That's what wave. Wireless access for vehicular environment. This is called as wave. So it has perfect examples there. So you can see these are all some of for the wave. That is for vehicular ad hoc networks. So you just to go to the examples folder, you can understand some good examples over there. You can see VANET routing compare. Similar like Manet, we have VANET routing compare. We have wave simple 802.11p. So if you want to use 802.11p, now in this example today we have seen 802.11b. So that is on 11 Mbps radio. Now here we have 802.11p, which is mainly for vehicular networks. So this also you can able to simulate it, or you can able to try out on VANET routing compare protocol. Okay, so this one, then what else? You have other things as well. Let's say if you want to go to AODV, I already showed you yesterday. So anyhow, we'll just go and show you AODV protocol, then CD, SRC. So if you see the source, sorry, CD model. So if you see it now, so you can see AODV, DPD, AODV neighbor.cc, AODV routing protocol.cc, AODV routing table.cc, routing queue.cc, then AODV packet.cc. So you have all the AODV protocol source codes are available. If you are planning to do your research on AODV, you can able to use the AODV protocol. Okay. So and we have 6LoWPAN also. So 6LoWPAN is mainly for the Internet of Things. So if you want to use Internet of Things, then you can use 6LoWPAN for that. So I'll just show you that also. You can see 6LoWPAN header.cc, 6LoWPAN netdevice.cc. So only basic things available, but for initial research you can able to use this 6LoWPAN. So you can see some examples. Example LRWPAN, LRWPAN mesh under, and example 6LoWPAN, and example LRWPAN beacon.cc. So likewise, just to go and check your source folder. So if you want to start your research, if you want to start your project, so you can start somewhere at the SRC folder. Okay. So these are all different things. And if you want to deal with antennas, so if you are from electronics background, if you want to deal with antennas, then you can use this antenna. So in this antenna here, so you can use antenna. No examples are there, but you have seen the angles, antenna model, cosine antenna model, and isotropic antenna, parabolic antenna, and 3GPP antenna array model. So we have so many antenna models also available in this. So these are some of the source codes available. So even spectrum also, if you need, you can go to spectrum and then check it. And OLSR we have seen today. So mesh network and LTE. So if you are in a 4G LTE, you can try out this. So plenty of options available for you to learn about NS3. And in case if you are really interested, because since this is should be hands-on, but there is no provision for hands-on. Had it been not in the pandemic session, you might be experiencing this by your own hand, so you might have understand it in a better way. But anyhow, I have more than 25 lectures related to NS3 in my YouTube channel. So please go on check my channel for all these examples what I have showed you in these 2 days. So here is my channel. So it is in the name of Engineering Clinic. So if you like my videos, maybe you just ping it, or you just subscribe it, so that whatever future videos I publish, you can able to get the glimpse of NS3. No sir, I want to do NS2. So NS2 also I have more than 30 hours of lecture. 30 hours of lecture. NS2 also in IoT and in Contiki OS. Contiki NGOS, I have around 10 hours of lecture. So more things are there in my channel, so you just refer my channel. And in case you want to send me an email, so my email address is pradeepkumarts@gmail.com. So any questions, you please post it in the comment box. So thanks for your time and understanding. Swati ma'am.
Hello, sir.
Yes ma'am.
Sir, Gururaj sir will join in a minute, sir.
Yeah, okay ma'am, okay.
Hello, Pradeep.
Yes Guru.
Yeah, it was really good. Actually, we thought of expecting the same workshop offline because of this
Okay,
pandemic. We could not able to have it. Anyhow, all the
okay,
participants are very happy. I think I had forwarded you the YouTube link also. You can check there. Many
okay.
people they have asked the question also, and
Mm-hmm.
it was really good. And thank you so much for your no wonderful session and accepting our invitation on behalf of computer science and engineering, and also on behalf of Wing Research Community. We wholeheartedly
Okay.
thank you for your wonderful session. Thank you so much, Pradeep.
Yeah. Thank you Guru. Thank you ma'am.
Okay. And from the Department of Computer Science, I take this opportunity to thank all the coordinators who given their complete efforts to have this workshop. Thank you, Swati, and thank you, Chetnamam. Thank you so much. We can leave now. Pradeep, I'll rest of the things will talk to you offline. Okay. Thank you
Yeah,
so
okay,
much.
okay Guru. Okay ma'am. Yeah, thank you.